Hi everyone, welcome to my talk, this unexpected talk. I didn't know this morning that I would be giving this talk, but it's a pleasure to be here and to present Quandela's roadmap to fault tolerance, starting out with the photonic platform. Just a disclaimer, for those of you who have seen Shane Mansfield's talk this morning, feel free to grab another coffee or have a quick 20-minute nap. I think you would have seen most of it. Not all, but most. All right. Let's start out. If I get this to work. This one. OK, indeed, there is a laser pointer. Perfect. So let's get started straight away. Quandela was founded in 2017. It's based on 35 years of academic research at CNRS. Shortly after the founding, they delivered the first commercial quantum device in 2018. Meanwhile, we're more than actually 120 people. We have about half PhD. Half of those people have PhD in diverse fields. We have 2 production facilities not far from here in Massy. We have 4 main locations worldwide at the moment. This number is growing, but these are the main locations worldwide: Canada, South Korea, Germany, and of course the headquarters here in Massy. We have scientific excellence with Pascal Senela, one of the co-founders, and Alain Aspect on the scientific advisory board. And of course, we are, as you would have also seen in the video, we are a full stack provider. So we do everything from hardware manufacturing. We assemble our own quantum processors. We have our own open source programming framework, Percival. And we look into quantum algorithms, and we have a cloud offering. Now, here you see, so we built cutting edge quantum computers. We have our own quantum computing factory where we assemble the QPUs, and we also hook them up to the internet so that people can access them via the cloud. So we have a quantum data center. We also have our own clean room where we fabricate the single photon sources, and we also grow our wafers. So this is the secret ingredient. This is a single photon source based on a quantum dot that sits at the center of this cross. So this cross, or this structure here, this microstructure, was etched out of a gallium arsenide wafer that was appropriately grown before. Just for those, most people, when they think quantum computing, they think gate-based modality. The question is, how does a photonic quantum computer work? Because it's distinctly different, at least in the most simple version, which is this modality that I'm showing you here. Sorry. So here we've got a single photon source, emits single photons at a time. In order to make use of the photons, we need to sort them. We need to multiplex them, or demultiplex them rather, and then sort them into these different spatial channels, making sure that they arrive at the same time at this photonic chip, where the magic happens, where the quantum calculation is actually done. So this is an interferometric chip where we can control the different paths through thermal phase shifters, which are these white diamonds here, and therefore control and set the unitary that this chip corresponds to. And so what happens is the photons propagate through this maze here, get entangled, and then are detected after propagating through the maze one by one, and we accumulate the statistics, and from these statistics we can then infer the result of the calculation. And in principle, this is a universal chip, so we can implement any unitary matrix with this method. In principle, it's high speed. The excitation rate of our single photon source is at the moment 80 megahertz. We believe we can go to 1 gigahertz. In principle, it's high precision. We can accumulate statistics very quickly and to the precision that we want. And the whole thing is robust to noise. Photons, of course, they don't decohere. They get lost. Okay, so we're not suffering decoherence in this context, but we're suffering photon loss, and that's the one single parameter that we always strive to optimize in the lab at all costs. All right. In principle, you see, so this is the first photonic QPU that was assembled in 2022. The paper appeared in 2024. You can find it here. The same architecture. We have the single photon source, the demultiplexer, then the universal interferometric chip. We have SNSPDs for reading out for detecting the photons, and then a correlator to read out the SNSPDs, and a classical processor. And the access or the control of the machine is done through Percival and through the Quandela cloud for the end user. This is what it looked like in 2022 for this paper, the measurements for this paper. But shortly after, the team managed to put this into a sort of a footprint of a normal rack. And the first QPU was delivered end of 2023 to OVH Cloud. Since then, we have deployed 4 more systems, and we're about to actually deliver a 12-qubit machine to Gensi within the Euro HPC call in about 2 to 3 weeks. So that's a big event, and team worked very hard to make that happen. Typically the assembly time is 10 to 12 months. The system, though, can be deployed and installed on site in 3 days. So it's ready to go in 3 days. It's simply socket. You need an electrical socket, and you can plug it in, and it works. And of course, it can go directly into HPC environment. It's robust to thermal and noise, and generally also very low energy. I mentioned several times Percival. It's our own open source programming framework, which we use to control and make use of the power of the machines. Now, applications, kind of one of the big mottos of this conference. We're also developing applications for our systems, and we co-develop software solutions for industry problems. We have a number of corporate clients. You can see them listed here. I'm not going to read them out. We work with them across topics like machine learning, simulations, optimization, and also cryptography. We have of course, we have a dedicated quantum algorithms team for that, and we have our cloud presence that can be used by the clients as well. We call this part of our offering the Quantum Acceleration Program, and you can find out more at our booth if you're interested. Now, just a bit more in detail about the currently deployed use cases and solutions. There's a lot going on in the hybrid quantum AI space. A lot of classification work that the team's doing. For example, I just pick one of these examples, which is in finance, where it's all about classification of fallen angels, and you can actually see that you can have some gain there with the quantum solution. Then I'm going to comment on that in a moment, on the generative AI application. And then we've got more sort of usual applications, for example, in terms of energy infrastructure modeling, energy grid planning, and also we have the OVH Cloud partnership is on cybersecurity. All right, so just a few words on the generative AI application. So this was in the context of the BMW Airbus Challenge last year, and the task was to for having autonomous vehicles, they need to be able to drive also during the night, not just during the day. In order to train them, you need night images, and there are not enough night images, so you need to generate nighttime images from your daytime originals. And what the team did in this case, they used 2 different approaches. They used the quantum GAN, where they replaced the layers between the encoder and the decoder with the quantum annotation method, and you can see the result here. And then they used the second approach, and by the way, this means boson sampling, okay? Just to be clear. So they used a combination of the classical GAN and the boson sampling machine, so the photonic QPU, to generate these images, and there they could show that indeed you can reduce the hallucinations in the pictures that you would otherwise get with just a pure classical method. But I'm myself not an AI expert, or machine learning expert, so please come to Xavier Pereira's talk, who will talk in more detail about this. He will also present our photonic quantum machine learning framework, which was developed specifically for AI people. to be able to use quantum functionalities. And yeah, you can check this link if you're interested, or come to Xavier's talk, or both. All right, so generally speaking, we're in phase 1, where we have quantum AI applications. We're looking in the next stage, when we scale up the number of qubits in our boson sampler, we look at these kind of applications, and of course, beyond 2029, when we expect to have entered the fault-tolerant regime, we expect to look into other application domains. In parallel, of course, while thinking about the applications, we also have a hardware roadmap, just summarized in this document here. Currently, we're here. This is the machine that we're delivering in a couple of weeks, Belenos with 12 qubits, but then we will double the qubit count each year. And what is important to note is that when you have a boson sampler, so this simple photonic quantum computing modality, once you hit something like 40 photons, a classical machine cannot simulate the outcome anymore. So we expect some interesting stuff to happen here, and for applications to emerge at that point. Now, if you want to go further, the boson sampler is not the right way, because you've got losses in the system and you can't scale your photonic chips infinitely. So you need a different modality, and this is now the road to fault tolerance, and relies on Quandela's specific architecture. So before I come to that architecture, of course, the usual standard way that a lot of people know is to use measurement-based quantum computation, and specifically fusion-based quantum computation, which is the way that our biggest competitor is actually following. So just in brief, Shane pointed out this morning already, that you need these logical qubit states. So these are 24 photons that are entangled in a specific way. You can create them by just using single photons and stitching them together to more and more complex objects, and then in the end, you end up with your logical qubit. If you're going all photonic and you're using parametric down conversion sources, you need an awful lot of sources to generate photons, and you also need a lot of optical elements to generate the fusion process that stitches together these photons. Overall, when you look at typical suggested architectures, what you see is that to generate one logical qubit, you need 1.6 million sources, and more than 1.6 million detectors and phase shifters, just to create one logical qubit. So it's very, very, very resource intensive. You can do better than that. You can use quantum dots in so-called micropillar cavities. You can use single photon sources from Quandela, in principle. So the power of the quantum dot sources is that they don't only generate single photons on demand, but in addition, the quantum dot can be charged with an electron or a hole, such that they carry qubits, or spin qubits. So they have spin, so they act as a spin qubit, and you can control this spin qubit in a coherent fashion using laser pulses. And that way you can also create multipartite entanglement at the source, okay, on demand. So if you choose the right laser pulses, you get a stream of entangled photons out here. And this has been nicely shown in Pascal's group, where they showed a high rate entanglement generation. Very recently, they were able to demonstrate the generation of so-called caterpillar states, which are a key resource for fusion-based quantum computation. I don't have time to go into that, but if you're interested, please come to Pascal's talk tomorrow morning. It's worthwhile, definitely, and she'll be talking about all these things in more detail. Now, as I said, you can use the quantum dot sources to generate, in principle, your logical qubit that you need for fusion-based quantum computation. How to do it is shown here. So you take a single photon source, but you don't take one, you take 12. And then you generate entanglement between the 12 sources, or the spins in those sources, using a repeat until success gate. So essentially, you use the photons emitted from the sources, interfere them on a small photonic chip, and that way you can create entanglement between the two spins. And typically after, I think, around 6 tries, you're sure that you have had a success. Okay, so that way you can entangle your quantum dot sources stepwise, and then you have these 12 sources in this entangled state. And then we were able to show that through 2 photon emission events from this entangled state, you can actually generate the logical qubit. And the amazing thing is that overall, the resources needed are much less than in the previous case. So you just have 12 sources, 24 detectors, and 24 phase shifters. OK, so this is about 100,000 times more efficient, this method, than in the other case. But actually, in fact, we don't actually want to do fusion-based quantum computation. We want to use our own architecture. And we have our own ideas how to realize that. And for that, we just need this state here. Okay? We just need an entangled state between the quantum dots. And so this is the SPOC architecture, spin optical quantum computing architecture. And this is in principle shown here. So you've got your sources. Sorry, I clicked too early. You've got your sources. You've got small photonic routers that are able to distribute your photons from the different sources to the different chips here. And then you've got these Rust gate chips. These are these entangling gate chips. But the advantage of these chips is that the complexity of these photonic chips compared to the boson sampler you've seen in the beginning is much less. So you've got hardly any losses. The path is really small in these chips. And that is a big, big advantage. The price you pay is that, of course, you need to use more photon sources. You need to use more of the quantum dot sources that we have. But we're experts on that, and we can deal with that. The other big advantage is that this whole architecture is very modular. It's interconnected. It's all fiber connected or optical waveguide connected. It has actually a low error threshold, and it's very energy efficient, the whole architecture. So just for illustration purposes, and because I like the animation, you can see how to build up a whole network here. So again, sources, routers, and then the different entangling chips. And once you've got a green light, you know you've entangled your quantum dots, and then you can build up a whole network through that. OK, so this is our architecture. And just for the experts, the quantum error correction experts, if there are any in the audience, so the team has first tried to implement the surface code with the architecture and also the Floquet code. And the nice thing and the message here is really the numbers that you get out here for the problematic quantities such as photon loss, photon distinguishability. You want the photons to be indistinguishable for this scheme to work. But so distinguishability is kind of the enemy. And also for the spin coherence time of the quantum dot, which is now important in this architecture, the numbers look actually quite promising. Nothing like 99.999% transmission. No, you can actually go to, for example, 94% transmission, which seems quite achievable. And the team is also in the process of simulating LDPC codes with the SPOC architecture, and the results look even more promising than what you can see on the transparency here. So just to wrap up, so as I said, the price you pay for having less complexity on the photonic chip side is that you need to take good care of your single photon sources. And we're experts at that, as I said. But we need to implement the industrialization of that value chain. And that's already in full swing. So we have already our own clean room in Massy, where we do all the steps for fabricating these single photon sources. Here you see a quantum dot that is pigtailed to a fiber, where we can just deliver the single photons out of fiber. But it's also important to note that at the moment, the first step in this value chain, namely the growth of the semiconductor wafer that we need for our process, this is not in Quandela hands at the moment. And so it's my task to build that up in Munich. I should have said, OK, so the industrialization, of course, you need to see that everything is, that you have redundancy, that the process is reliable, and that you have high enough yield. And the idea is to not only have that in this part of the chain, but also in this. And so what we're doing in Munich is we're building up MBE machine to produce these semiconductor wafers, and it's my task to build that up, and also to build a quantum algorithms team, and of course also a business team alongside it, so that we have a a thriving subsidiary there. And with this, I'd like to thank you for your attention, and I'm happy to take questions maybe after the talk or outside. Thank you very much.